So, good afternoon to everybody. My name is Fabrizio Ramoino. I work at ESA Earth since 2011 as optical high resolution and thermal exploitation expert. So, during the presentation of today, I will introduce you the optical instrument, the interaction of electromagnetic radiation with the surface, the interaction with the atmosphere and how to apply correction, the pre-processing of optical data, and an introduction on why use time series and how to retrieve radiometric indices for water, and a couple of examples of hazard monitoring using remote sensing data. Later this afternoon, I will provide you even the practical using SNAP on applying SNAP on Sentinel-2 data in order to retrieve water extend and water mask in order to monitor the water change detection. So remote sensing is designed to obtain information on that surface without coming into direct contact with it. So we need a source of energy and illumination. In this case is the sun for optical instrument. And after we have the radiation and the atmosphere. We have our target object, that is in this case is a flower. The radiation coming from the sun would be redirected, part of the radiation will be redirected to the sensor. That could be a satellite, airborne images, whatever. And after there is the transmission to the ground segment that is in charge of processing and distribute the data. And after there would be the final product that linked to the application, in this case hydrology or even land use, land cover, and whatever. So this is the spectrum. The optical radiation, so the visible wavelength is very narrow, and this comes from 0.3 till 0.75 micrometer, and this can be perceived by the human eye. After we have the near infrared, that is very sensitive to the vegetation. We have the thermal infrared to detect hot surface like fire, active fire, or even volcano eruption. And after we have the microwave, so the SAR. Sentinel-2, we start from the visible till here, shortwave infrared, around 2 micron. So the optical satellites are passive respect to some SAR satellite that are active, so they send the pulse and they receive the response from the object. The optical satellites take the radiation emitted by the objective. They use devices that are quite simple. They have a camera on board. They observe the surface of the Earth across a varied spectrum of wavelength. We have different kinds of satellites. For instance, Sentinel-2, it has on board 13 bands, but we have Spot that it has 4 bands, if I'm not wrong, till the near infrared. But we have even hyperspectral satellites, sensors that have more than 200 bands on board. And in this case, you can distinguish even different kind of crops or vegetation type. One example is the Shine that will be launched in 2028, if I'm not wrong. So the optical imagery is more, it's easier to interpret because it's natural color. In the image above, on top we have the natural color RGB, and we have the same area with a combination of near infrared, false color infrared. And you can see that the vegetation is very bright red. respect to the crops field here. We have two kinds of optical scanners. One is a cross-track that was used in Landsat up to Landsat 7. And we have now Sentinel-2, Landsat 8, and Spot use a long track. Is the second image, this one. So they have a fixed scan with different detectors, and they acquire the image in the same time. So the optical and remote sensing over the past 40 years had a big evolution. So in terms of spectral resolution, for instance, Sentinel-2 has 13 bands, respect to Spot that has 4 bands. Spatial resolution, because we have satellites that has a spatial resolution less than 1 meter. The radiometric resolution, we pass it to 16 bits with Sentinel-2 satellite. The temporal resolution is the temporal coverage, the revisit time of the satellite. This depends on the spatial resolution, because more is the spatial resolution, so more deep you see the pixel. So if you have 1 meter pixel spatial resolution, you cannot have a swath width of 300 kilometers like Sentinel-2. Sentinel-2 has a resolution of 10 meters and has a swath width of 300 kilometers. So it means that every 5 days you will get the revisit of the same place on the Earth. If you go up to the north, you will have more frequency because it's a quasi-polar orbit satellite. And after you have also other remote sensing instrument like unmanned aerial vehicle, in situ instrument. In order to these are very important in order to validate a product. So this plot represents what I was telling you before. So if you have a spatial resolution of ½ meter, you will have annual revisit time. If you have 1 to 5 meters, you have monthly revisit time. If you have, in this case, the Copernicus constellation, Sentinel-2, Sentinel-1, you will have weekly revisit time. And after, you will have also other satellites like Sentinel-3, MODIS Terra, and MERIS, or Spot Vegetation, that has a resolution of 300 meters, 1 kilometer. For METOP is 5 kilometers, if I'm not wrong. And there you can have a revisit time, a daily revisit time. With Sentinel-3, with 2 satellites, you will have a revisit time of less than 1 day. And for instance, in my job, I'm involved in the Sentinel-3 Warfare Atlas. That is an atlas of fire detected by Sentinel-3, and we will have a revisit time of 1 day. So each day we can detect an active fire on the globe. So this is the eye revisit time for Sentinel-2 and Sentinel-1. This is old because we don't have any more Sentinel-1B, if I'm not wrong. So this is the revisit time for Sentinel-1 is around 12 days. And for Sentinel-1 is 5 days. If you go up to the north, is less than 3 days. This is the improvement in terms of resolution. On the right side, there is Landsat, this 30 meters spatial resolution. And on the left side, there is Sentinel-2. And this is very important for field monitoring. So these are the bands of Sentinel-2. So we have 4 bands at 10 meters. So the visible plus the near infrared. band 2, 3, 4 at band 8. We have 6 bands at 20 meters spatial resolution. We have 3 bands in the red edge. And these bands are very important to distinguish different kinds of crops. We have a narrow band in the near infrared, band 8A. And after we have the 2 SWIR bands that are very sensitive to the hot surface. Using these 2 bands, you can detect a burned area during and after the active fire. And after we have 3 bands at 60 meters. These bands are used for cirrus correction and atmospheric correction. This is the difference between the bands of Sentinel-2 on top, and after we have Landsat 8 and Landsat 7. So we don't have the thermal bands that were on board of Landsat 8, but we have we improved the spatial resolution to 10 meters for these bands, and we introduced the bands from 5 to 7, the red edge bands, for crop monitoring. The rest of the bands are very similar to Landsat, in order to provide even continuity and to work together with Landsat, even if the spatial resolution is different. So this is the interaction with the surface. So we have our source of energy is the sun that go to the surface, and there is a part of this source that is absorbed and transmitted to the ground, and part of this is reflected and this part is the one detected by the sensor, by the optical sensor. So this is the part of reflected energy. It depends from the type of material, the nature of the surface, if it's flat or roughness, the wavelength of the incident radiation, and other factors. So this is the spectral signature of water. So this is the visible, and the absorption coefficient for water is very low. And after, starting from near infrared, there is a peak of the absorption coefficient. It means that in the near infrared images, the reflection of the water surface is very low. And in fact, if you open the near infrared band on Sentinel-2, the water looks like black. It's very dark. So this is the interaction of liquid water and visible infrared and thermal infrared. As I say, so there is the absorption for the visible bands, for the bands used in the visible for Sentinel-2 is very low, and after it increases in the near infrared wavelength. So this is interaction of real water bodies and visible. So there are several factors, as I said before. So there is the reflection, refraction, but you have also particles in the water, like phytoplankton, cyanobacteria, deep water with other particles. So it's quite difficult to characterize very precisely this kind of the quantity of absorbed energy and the quantity of reflection energy. This is the reason why we have the in situ measurement, in order to calibrate and validate the satellite measurement. This is the interaction of water in the atmosphere and the visible infrared. So absorption can be caused by vapor, gas, or scattering by droplets, so liquid and ice. This is the spectral signature of bare soil. You can see that it's quite different from the water. So the incident radiation can be only related to soil-atmosphere interface, influenced by soil structure, and reflected slightly increases from the visible to infrared bands. This is the visible range. This is the infrared, more or less. So the spectral response the spectral signature is quite different. This is for the green vegetation. This is very complicated because we have the leaves, and each different kind of leaves provide different kind of reflection. So this is in this case, the in situ measurement it's needed, because in order to characterize and to distinguish the kind of vegetation that we are observing. The vegetation has a high reflectance response in the near infrared, in this range, and not so high in the visible. This is the comparison between Sentinel-2 and Landsat, the spectral bands. The red line is the soil, the green is the vegetation, and the blue is the water. Here, the 3 bands for the crop monitoring, it's exactly on this spectral range, wavelength range, where the vegetation and the soil cross each other. And this is very important to distinguish which kind of crop field we are observing. In Landsat, we don't have this information. So in order to work with optical data, we need to apply some pre-processing. I will show you during this afternoon, during the exercise. So on optical, in respect to SAR, we have the problem of clouds. So we need to detect the clouds and to remove. And there are several of algorithms that do it. And after, we have to apply the atmospheric correction, reprojection, resampling, and co-registration. I will go one by one and I will describe. So the first one is cloud detection and removal. So usually when you go on well-known area like Congo or even Belgium, in full year of observation, it's easily to not find a cloud-free image, even a cloud-free pixel. Some years ago, in 2015, we had an exercise over Belgium, and over 1 year, there were portions of Belgium that were not covered by Sentinel-2. And in that case, we had only one Sentinel-2 satellite, so the revisit time was 10 days. And the same case was over Congo. So an image pixel can be cloud-free, so free of cloud, partially cloudy, or totally cloudy. The cloud detection methods can be distinguished by the following class. So spectral threshold methods, so you can define a threshold value, and after you can test the spectral characteristics of the image, like temperature, brightness, or whiteness, or height of the scatter, and test with this threshold value. Another one is the feature extraction and classification. So this is based on statistics and on a stack of images. And after, we have a learning algorithm, so based on cloud probability or cloudiness index value. A multi-temporal analysis, so you have a stack of images and you fill in the gap with the cloud-free pixel. So you remove the cloud based on some of the methods seen before, and fill in the gap with a cloud-free pixel. And after we have multi-sensor approach. For instance, when you are working over Africa, you want to have a cloud-free image of Africa, you need to complement Sentinel-2 data with Landsat data maybe, or even Spot. It depends from your sources.
Sorry,
yeah.
Cloud threshold. Is there a common number, percentage for them? We decide, for example, 20%, 30%. Is there a common?
It depends. Yeah, it depends from the structure of the clouds, and it's much easier using the thermal. Thermal instrument can provide you a good response if it's cloud or not, because there you have the brightness, temperature, and when there is the cloud, it's easily to detect.
Because usually when we are crossing the data, we have to put a threshold, remove some images, which, for example, those are more than 40% of cloud pixels. Okay. But I have not seen in the literature a common number.
Do you mean an image affected by, the image is affected by 40% of clouds? Yeah. In this case, it depends from your application, because if you are limited in terms of number of images, you need all the images that you have. So you can remove the clouds and fill in the gap with the next image, the image on the next acquisition. But we have, after this, maybe I will show in this presentation that there are several, even for instance, Sentinel-2 core that is used for atmospheric correction on Sentinel-2. The output of Sentinel-2 core is the cloudy pixel, so it's a cloud mask. So you can extend even the buffer of the clouds, and you can remove quite easily the clouds and fill in the gap with the next image. Yeah, this is the interaction with the atmosphere. We have the scattering and the absorption. The scatterings occurs when particles or large gas molecules present in the atmosphere interact with and cause the electromagnetic radiation to be redirected from its original path. And the absorption, it causes molecules in the atmosphere to absorb energy at various wavelengths. So we have to compensate these atmospheric effects with, with this one. So at the sensor, reflectance is the surface reflectance plus atmospheric reflectance. We miss this part. In order to give back this, to add back this part, the atmospheric reflection, we need to correct atmospherically the image, the top of atmosphere images. Yeah, this is the effect atmospheric correction. So aerosol optical thickness has a contribution of 80%, water vapor about 15%, and altitude about 4%. These are the cloud detection and removal algorithm. As I said before, we have the Sentinel-2 core, that is the one used in the payload and data ground segment at ESA. It's for atmospheric correction and cloud detection. So it uses input level 1C, that is top of atmosphere, and it provides as output the bottom of atmosphere, so adding back the atmospheric effects, plus several masks as well. We have the aerosol optical thickness map, water vapor map, and scene classification map. This scene classification, there are, if I'm not wrong, 10 bands. For land, water, cloudy pixel, partially cloudy pixel, cirrus cloudy, snow, and even other, maybe saturated pixel. After we have Maya, developed by CNES. This is based on a multi-temporal processor. It means that you need multiple images. The Send2 core work on a single image. The Maya work on a stack of images, but you need as input, as first input, to train the algorithm a cloud-free image. There is the IDPix developed by Brockman Consult. This is on Snap as well for cloud detection. We have the FMask developed by USGS, and this can be applied on Sentinel-2 and Landsat as well. And after we have the Sentinel Labs cloud detector. That is a combination of FMask, Send2 core, and Maya. The most common is the Send2 core because it's the one used from ESA, and all the Sentinel-2 level 2i products have been corrected by using Send2 core. If you go to the TEIA website, the one from CNES, you will find the Sentinel-2 images over France, more or less, even over Europe, corrected using Maya. So if you cannot use the Sentinel-2 images corrected atmospherically from Send2 core and Maya together, because there are some difference in the lookup table or some parameters are different that you cannot compare in your application. So you should decide, you should choose one of the atmospheric correction and apply this over all the images that you have. So this is an overview of Send2 core. So it's a single image processing algorithm. This is take as input level 1C and use DEM and lookup tables, and give as output level 2A products, bottom of atmosphere. So it applies cloud screening and classification, atmospheric correction over land surface, using Libratran lookup tables. This algorithm is included in Snap as well as plugin, external plugin. You can download and install Snap and run your the atmospheric correction over your stack of images. Yeah, this is the output. So 11 bands at 60 meters, 9 bands at 20 meters, 4 bands at 10 meters. And after you have the Arrow's optical thickness map, water vapor, and classification map. For the bands, you have the 4 bands at 10 meters. The 4 bands at 10 meters, you will have at 10 meters. And after 9 bands at 20 meters, because you will have again the 4 bands at 10 meters in 10 meters, plus the 6 bands minus the 8A, that is the narrow near infrared bands at 20 meters. And after you have the 60 meters bands. For the cloud screening and classification, Send2 core imported the ESA CCI land cover map developed by UCL, University Catholique de Louvain, at 300 meters, together with the water bodies as no occurrence. This is used in order to detect the clouds. This is without ESA CCI inputs, and this is with ESA CCI inputs. Yeah, as I said, this is the classification map. So you have no data, saturated pixel, dark area pixel, cloud shadow, vegetation, non-vegetated, water, unclassified clouds, thin cirrus, and snow. So this is the inputs, level 1C, and this is the false color composite using these weird bands. You will have a scenes classification map, that is this one. And after you have the corrected output, atmospherically corrected output, and you have the aerosol optical thickness and water vapor. So the other pre-processing steps are the reprojection. So if you have in a time series a stack of images that from several sources, maybe the coordinate reference system is different. So you need to reproject on a common CRS. The resampling, because maybe you have, if you use Sentinel-2 and Landsat, you have different spatial resolution, and you have, if you want to compare and apply the same processing to both of the images, you need to resampling at the same spatial resolution. For the resampling in SNAP, we have three methods: nearest neighbor, bilinear interpolation, and cubic convolution. And after, there is another step that can be useful, it's the co-registration. Because if the satellite is the same, not always, but 90% of the case, there is no shift in geolocation. But if you use different data from different satellites, the geolocation accuracy is different. For Sentinel-2 is 1/3 of the pixel, it means 3 meters. But even if you have the same uncertainty on Landsat, you will have 30 meters divided by 3 is 10 meters. It means that Landsat compared to Sentinel-2, there is a shift of 1 pixel if you work with 10 meters. Why using time series? So time series, okay, is a stack of satellite images taken over the same area of interest at different time. We use this because for understanding how Earth is changing, for determining the causes of the changes, and for predicting future changes. And even if you want to produce a map, land cover, or whatever over a certain region, and you don't have a full coverage of that region, or maybe a cloudy pixel, you need a stack of images, a time series of images. I will show you during the exercise a time series over Lake of Bracciano in Italy to detect the water level change along 2 years, if I'm not wrong. So this is an example over a dam in South Africa, the water change. This is Sentinel-2, and you can see the water change here, top left. This is 1 year of data. So within 1 year, the water extent decreased drastically. Okay, it's almost finishing the video. So the white line is January 2017. The red one is January 2018, and there is a big difference, especially in the northern part, but even in the eastern part of the dam. Another application could be the deforestation. This is Rondônia region over Brazil, and among the years there was a huge deforestation on this part, and even here. So we use the time series to produce in several applications. One of these is the CCI land cover. So we started in 2005 with clock cover, 2009, taking all the available images for 1st of January 2004 till 31st of December 2004. The same for 2009. After we produced the epoch using 5 years of data, 2000, 2005, and 2010. And after we produced the yearly maps from 1992 using spot vegetation at the beginning, and after Maris, and spot again, and Sentinel-3. And now is a service of Copernicus, of the Commission. We produced even some high-resolution land cover map over Africa and Mexico and Central America using Sentinel-2. The African one is at 20 meters and is a prototype because it wasn't validated. The second one, there was a cooperation with the Mexican Space Agency, and we produced the map over that area for 2016 and 17 at 10-meter resolution, and this map has been validated by our colleagues in Mexico. The new product, we released this product late 2022, if I'm not wrong, is World Cover 2021. It's a world land cover map at 10-meter resolution. Has been developed by Vito using Sentinel-1 and Sentinel-2 constellations. And to process all the data, they needed a lot of time to develop the processing chain, but to process the data on Amazon Web Service, it took 4 days. This is radiometric indices that you can find on SNAP. You have vegetation indices, soil indices, and water indices. In the exercise of this afternoon, we will use the NDWI-2 index that is very important, was developed by McPheeters in 1996 to detect surface water in wetland environments. And this is an example of a lake in Iran, if I'm not wrong, using NDWI-2. So you can distinguish the water from the rest of the vegetation soil. Another one is this one. This is the Sentinel water mask. This algorithm was presented by a Polish students in the ESA Land Training course 2017, and that won the Best Poster award on the optical remote sensing category. And this is, together with the other one, with the other radiometric indices, will help us to define the water extent. So we will use this, usually the NDWI-2 over 0.3. If the value is over 0.3, it means that it is water. But it depends on the environment that we have. We use also this mask in order to distinguish properly the water. This is the NDVI, so the Normalized Difference Vegetation Index, that I think that is the most famous index in all the remote sensing area. So it's a ratio between the difference near infrared and red bands, and near infrared plus the red bands. And using this index, you can define easily what is vegetated and what is not vegetated. Another one is the Normalized Difference Moisture Index using Sentinel-2. I presented this index last year in the previous land training course, because it was mainly related to agriculture and water resource management. And this is, using this index with Sentinel-2, you can improve the algorithm, because usually Sentinel-3 is used for soil moisture using the thermal bands. But there you have a resolution of 300 meters. Using NDMI, you will have a resolution of 20 meters because you have the 10 meters band here and the SWIR bands that is at 20 meters. So the output at the end, even if you resample, but the initial output, the initial input band was at 20 meters, so the output is at 20 meters. Okay, this is just an overview of water cycle. So how the remote sensing can see the state variables one. So water surface can be detected by radar backscattering or optical thermal. Water body volume by proxy, water surfaces. Soil moisture by microwave, and even Sentinel-2 using the previous radiometric indices. Ice and snow cover by optical and thermal and microwave, active and passive. Snow water equivalent using microwave, active and passive. And the water quality using optical and thermal. Okay, for the precipitation, we have radar and cloud properties with the thermal. Evapotranspiration using Sentinel-3, so the thermal and the visible, and stream flow, surface runoff, so proxy. And at the end we have, okay, this is infiltration, regional water balance, seepage is thermal, and yeah, this is in general simple and complex fluxes, the integration by remote sensing and models. So here I put two examples of hazard monitoring using remote sensing data. Okay, this is the geostationary orbit for satellites to detect precipitation. So we will have geostationary that have high temporal resolution, 15 to 30 minutes, but you have a very low spatial resolution, from 1 to 10 kilometers. And after you have the quasi-polar orbit satellite. An example is Sentinel-2, for instance. So you can improve the spatial resolution, but the temporal resolution is till 14 days. So this is a description of the event on Emilia-Romagna on last May 2023. So 350 million cubic meters of water within 36 hours, and affecting 100 municipalities. This is the system, the Safer Places platform, co-funded by ESA incubated program, and within the civil protection of Emilia-Romagna region, they use satellites like Copernicus Sentinel-1, 2, Cosmos SkyMed, Planet and Spot, plus integrated in situ data coming from Emilia-Romagna civil protection. And the outcome was, this is the affected area, and this was the effect using the remote sensing data. On the left side you show the water depth over Faenza, and on the right side there is an estimated economic losses for residential buildings. So the one in red has been affected by the floods. The other one is this one, the other municipality is Molinella, and this is the same as before, the water depth here on the left, and the estimated economic losses here. Another example of 10th September, if not wrong, was Larissa in Greece. So this is the city was affected by a big flood, and this was the effect of the flood. So all the crop fields was affected by the flood. And even this was the 31st of August. This was the 10th of September, and this is the 20th of September. So you see, respect to the first image, on the eastern part and on the north part, there was water, and it's dark water for all the sediments that that the flood bring with it. And that's it, I guess, yeah.